So we began today looking at the airliner that was made by Boeing 780, the 787 Dreamliner taking off. And, in addition to looking at how research is done, with like, for instance, the Large Hadron Collider and smashing particles, there's so much practical application to physics. And, looking at motion and being able to understand motion is very critical. And so we used aviation as kind of our example and use of this in real life. So we know acceleration is the change in velocity in period of time. And so what we're going to do in this one here is practice this aircraft taking off. So let's say that the aircraft initial velocity is 0, and let's say that it takes off v final of 63 meters per second, and so it takes off. And let's say that it takes 12 seconds. So what I want you to do is to draw the velocity time graph and then also solve for the acceleration of this aircraft as it takes off. So go ahead and pause the clip and do that. And when you're ready to check, you can hit play to continue. All right, so for your graph, we're starting at 0 meters per second, and then we're ending at 63 somewhere up here. And so the graph's going to look like this. The time period is 12 seconds. And acceleration is a change in velocity over time, which is v final minus v initial over time, which is the final velocity, which is 63 minus 0 over 12 seconds. And so we should get 5.25 meters per second squared. And if it's in this direction, it'll be positive acceleration. Now we could also get the slope of the graph. Remember, rise over run. So the rise is velocity, the run is time. So rise, run, and we get the slope as the acceleration. So one of the things that we looked at, with this section was how aircraft, as they land on a runway or take off on a runway, you got to make sure that they're long enough. This is the aircraft or the airport diagram for Jacksonville International. This runway is 10,000 feet long. This one's 7,700 feet long. And depending on the aircraft, they're going to have to use particular runways based on their landing and taking off capabilities. Now, on your equation sheet, you have the 3 constant acceleration equations. And these are very, very useful. Now, remember, speed equals distance over time only works. Same with the velocities delta x over t. Only works for the constant speed. If speed is changing, you can't use these because it's accelerating. You have to consider the acceleration to know what's going on with the motion. And so we'll practice this one here. We're driving through town, 12 meters per second. Ball rolls out in front of you. We apply the brakes and decelerate at 3.5 meters per second squared. How far do we go before stopping? Now, if you notice in this question, there's nothing to do with direction. You're going to have to define the direction. So here's the car moving this way. And they're moving through the town at 12 meters per second. So V initial is 12 meters per second. V initial positive 12 meters per second. And we apply the brakes and decelerate at 3.5 meters per second squared. Now, if we set this up as the positive x, this is the negative x, acceleration is this way, therefore it is negative. So you're just going to have to set up, a picture based on the situation. Quite often we'll have it just in terms of, have it in terms of speed or whatever, and then you just got to define the direction. We apply the brakes and come to a stop, so v final is 0, and we want to know how far do we travel, which is delta x. So what you do is you go to your equation sheet and look at the first one, say, okay, will this one give me what I want? Do I have what I need? And then, if it works, great. If not, you move to the next one. If the second constant acceleration equation works, use it. If not, move to the third one. One of the 3 should work. So go ahead and pause the clip and use your equation sheet. See if you can figure out how far it'll go before stopping. And when you're ready to check, you can hit play to continue. Okay. So it should go 20.57 meters as it goes. And then when it's traveled only half, the distance is the next one here. So when the car is only gone halfway here, what is V final? And that's what we're looking for in this one here. Now you have the same V initial. you have the same acceleration. And your delta x now, however, is halfway, which is 20.57 divided by 2, 10.29 meters, halfway. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we should get 8.48 meters per second would be what it is halfway. All right, now another thing that we'll want to practice here is, if we have a ball falling from rest off a cliff, we want to figure out how long is in the air, how much time, and then what's the speed when it strikes the ground, speed and velocity. So let's go ahead and set it up. We've got our ball. Here it goes. And our delta x as it falls will be negative 120 meters. V initial is 0. Acceleration is negative 9.8 meters per second squared. And we're looking for how much time does it take to reach the ground. And then for this one, how fast is it when it hits the ground? You can work through that as well. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so it should take 4.95 seconds, and the impact speed should be 48.497 meters per second. Now, this looks a little bit different than your equation sheet. Delta x equals v initial times time plus 1/2 at squared. The initial velocity is 0, and then the acceleration is negative 9.8. This is negative 120, and you should get a time of 4.95 seconds. How about if we throw a ball in the air? Well, as you throw the ball in the air, v initial is positive 20 meters per second here. And what do we know is true at the top? Well, v final is 0 at the top. And we want to know how long is the ball in the air, how much time does it take, and we know acceleration the entire time is still negative 9.8 meters per second squared. And yeah, and then also how high does the ball go? So you can do that as well. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so it's going to spend 2.04 seconds going up. And then the full time will be up and then back down, so 4.08 seconds the full way. And then how high does it go? You can use the final velocity equals initial velocity squared. Well, final velocity squared equals initial velocity squared plus 2a delta x, or you could have used v final equals v initial plus acceleration times time. However, you just have to be careful to use 2.04 seconds here because that's the time where it's going to be at the very top. All right, this one's a practice of a displacement. Person travels 16 meters per second east, then goes 8 meters south, find the displacement. Now, if you remember, it's critical here to draw your coordinate axis first. And then we always start from the origin, so 16 meters east first, then 8 meters south, and then the resultant would be here, and we can get the angle theta. Now, what you can do here, you're going to get blank meters, blank degrees, blank of blank. And so yeah, go ahead and give this a try. And calculate, the overall displacement. Instead of walking here and then walking down here, you could walk straight there. And what that would be. Now remember, this is where you start. This is where you go. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, 17.89 meters is the displacement from here to here. The tangent is opposite over adjacent, so the opposite side of the adjacent side, and we can get the angle. So Pythagorean theorem here, a squared plus b squared equals c squared, and we start on east and go south. All right, now with relative motion, this is where we're dealing with, let's say we're going with the current. We would put the tail of the VW vector on the tip of the VS, and the resultant would be like that, right? Relative to the shore. Let's say we're going upstream. If we went upstream, This would go on the tip of here, and this would be the resultant. Or, you know, across the stream, right? If we had it going like this, that would be the resultant. All right, so now let's take a look at projectile motion. This will be the final thing for today. Let's say that we have a person that throws a baseball perfectly horizontal, and then it flies out and goes like that. Now, one of the things that's critical to remember here is that the x velocity stays the same the entire way. So if you look on your equation sheet, this is the only equation that's under projectiles for x. And that's because there's no acceleration. Vx in this problem is 13. We want to know how far does it go from the base. And we also don't know time. Now, if you remember, if someone were to drop a baseball at the same time that was thrown, it's going to take the same amount of time to fall. And so if you remember, if you perfectly throw something straight out or something's perfectly thrown straight out, Vy initial is 0. And that's a critical part here because it starts at 0, but when what happens? It gets greater, and greater as it goes down, but initially Vy is 0. So what you're going to want to find is time using the y equation, and then once you do that, you can figure out how far it goes. So go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. Okay, so we should get for our time 4.52 seconds, and it should go 58 meters. 58.73 meters will be how far it goes.